I'm Agnip Sinha, and I'm a master's student at UIC. And I've built a large language model encoder project using distributed objects with AWS. And I'm going to briefly walk you through the project. Uh, Please bear with me. So I'll just give a brief introduction about this project. This project is mainly focused on creating an LLM encoder uh, from scratch with given data sets for using distributed computing in the cloud. We are using the Hadoop MapReduce functionality for embedding for generating embeddings of tokens of a large corpus of text. And we'll later use the MapReduce functionality to also find similarities between words. The distributed computing is primarily being handled by AWS Elastic MapReduce, which is the AWS EMR. Going over on the project overview, there are various steps involved in this project. The first one, as is similar with any kind of machine learning project, is data cleaning. We are preparing the text corpus for processing. We are sharding the data, the huge amount of text corpus, so that it can be easily processed via the MapReduce functionality of Hadoop and EMR. We are using MapReduce jobs. We are using four MapReduce jobs. One is to calculate word frequencies in the large corpus of text. One is to generate tokens for each word. The third part is to train embeddings using neural networks. I'm using TensorFlow for this, and we are using MapReduce for this as well. And the fourth one is we are finding similarities between words using the embeddings. And one additional detail, I am using the skipgram model, and I've designed it from scratch in Java TensorFlow, which I'll show you in a few minutes. Before I move on to demonstrating the code, I just wanted to give a brief overview about what this project aims to accomplish. The goal of the project is to build a LLM encoder, and this is the first part of three projects, uh, which will the rest two will follow after this. And the main idea behind the project is to showcase how distributed computing can help in heavy resource intensive tasks such as training and encoder, an LLM encoder, which if we were to try to do in our local machines, it probably would take a huge amount of time. Okay. Coming to the code, this is the code is written in Scala, and we are using Hadoop MapReduce. The Before I begin, I just wanted to show the build.spt. The Scala version is 2.12, and I'm using Apache Hadoop, and I'm using the 3.3.4 version, although I'm running the code in Hadoop 3.3.6, and I'm using JTocket to tokenize the data. And yeah, I'm moving straight to the main file, the main method, the main object, basically. So what it does in the main object is when I'm running the jar file, I put in 9 arguments. I'll explain the functionalities. The 9 arguments are consisting of HDFS locations or HDFS directories. I'll explain the functionality of each of this directory in detail. And we are running all of these tasks one by one. First of all, I'm counting the word frequency using a MapReduce, which I'll show. Next, we are sharding the text file and for the tokenizer, which is again a MapReduce functionality. Then we are taking the tokens and again sharding it. We're basically processing the data so that the embeddings can read it in a format that they are supposed to be read in, basically, to generate sliding windows, which are required for training the encoder. So, yeah, I'm performing the shardings for the embeddings, and I'm running token embeddings, which is using the third MapReduce in this project. After getting the embeddings, I'm merging the embeddings output. It's just yeah, just merging it for readability reasons for myself, basically. And the fourth and the last MapReduce is being run in the similarity analysis, which finds similarities between words based on the resultant token embeddings. I'll briefly go through each of the MapReduce. The first one is word frequency. So it uses a mapper and a reducer, of course. What is happening is in the mapper, it is taking the text and it's incrementing. It's basically putting a key value pair as in like word and one, the number one. And in the InSum reducer, the all the ones are getting summed, and basically that's how we get the frequency of the words. We are running it using run job, and yeah, that's pretty much it. Next is tokenizer. Tokenizer, I've created a separate one for word frequency and a word tokenizer because I'm maintaining the order in for the embeddings to actually make sense of the data. I am generating all the tokens in order, and that's why I have created two separate map reducers. The first one is basically doing the frequency, and the second one, this one, tokenizer MapReduce, is generating tokens in an ordered fashion. For this, I have used a mapper and a partitioner and a reducer. So, and yeah, I'm again running the job here. Uh, the second one for embeddings is I have taken the output of the last one of the last tokenizer and I'm feeding it to the embeddings, and it is generating it's basically training the encoder and generating the embeddings on a TensorFlow model, which I'm about to show the code of. Here is also a mapper and reducer. And one important thing to note is this functionality requires a window size, a stride. Both of these are for generating the sliding windows, and a vocab size. So vocab size is basically the maximum number of tokens. So okay, this might be a good time to show what the configurations are. These are the configurations. I'll explain all of them. Number of shards is for the first input for the tokenizer, how many shards are getting created. The second one is window size and stride, which I just showed. Number of shards for embeddings, which are basically how many shards are generated for the embeddings. The vocab size, I've defined it here because that is the maximum vocab size that is being formed in my case. Epoch is basically a machine learning, like how many times the iterator, and the score will update and the gradient descent will happen. So yeah, this is the epoch and this is the embedding dimensions where basically how many the vector dimension of the embeddings. I've given it 10. Initial learning rate is basically the alpha in case of machine learning, which we call as. I've given it 0.01 and it is written as initial because it will gradually decrease over time, uh, depending on how well the gradient descent is actually performing. Decay rate is basically by how much the learning rate will decrease. And decay steps is basically in how many epochs, sorry, in how many iterations the learning rate will decrease. Patience, I'll explain in a while. It is also related to the TensorFlow LLM. So yeah, going back to the embeddings.mr, sorry, embeddings.mr, you can see that we are generating the windows from a get windows functionality, which is in the utils package. It's right here. Okay. Next thing is we are getting the learned embeddings, basically. Embeddings generator is, yeah. This is the code for the TensorFlow, basically. I won't go into too much detail about this, but I've created the model from scratch. There was no predefined model for this. So including the gradient descent, I have basically written everything. This is a skipgram model. Uh, I'm using a skipgram model. There are many multiple models that are available for LLM training, basically training the encoder, and I've used a skipgram model in this case. This is the loss function. I've defined it explicitly. And this is where this is for the gradient descent and number of epochs. And I'm running the epochs one by basically. I've used a for loop in this case explicitly because the epochs are not mapping anything, right? So I've used a for loop in this case explicitly, and yeah, that's it. And the patience is basically to check for premature stopping of the training. So if say in this case it is 10. So if say in 10 different occurrences, the loss has reduced significantly. And so if the 10th time that it is being reduced, we are stopping the um, learning and we are just exiting from the learning basically and returning the embeddings, the learned embeddings. This is for this. And finally, this is the similarity map reducer. What it is basically taking um, all the embeddings that is being generated from the last map reducer and it is comparing one against each other and it is basically finding the top 5 best similar words of each word. That is its goal. We are in the mapper, we are taking the similarity for each and every token to token pairing. And in the reducer, we are taking the just the top 5 similarities, and we are writing it to context. So I'll just show you this is the function where the similarities are being generated. calculated. And yeah, it's a cosine similarity. That's it for this code. Yeah, I'm going back to main.scala and I'll just go through what each of these arguments mean. Input is where the input file is stored. The main file. Word count is basically the output of the word frequency MapReduce. Tokenizer input is input for the tokenizer MapReduce. Tokenizer output is for the output of the tokenizer MapReduce. Merge tokens is where I'm merging all the tokens and putting it in a file. Sorry, in a folder, in a file in a folder, the which is the merge tokens folder. Embeddings input is the input for the embeddings MapReduce. Embeddings output is for the output of the embeddings. Um I'm storing the all the files in embeddings output, merging them and storing them in merged embeddings. I'm not taking input folder for similarity. I'm giving the embeddings output as the input for the similarity, and the output is the final output, which is basically the similarities that are being generated. You can see in the similarity runner, I'm giving the input as the embeddings output and the output as the output. Yeah. So this is it for explaining the code. I'll quickly hop onto the AWS EMR, AWS interface. Oh, one thing I forgot to mention. I've already created the jar file, and it is stored in just a sec, the S3 bucket. I'll just show all my buckets. These are the two buckets I have, and it is stored here, the jar file. So now there are a few preliminary things I'd like to talk about. So, yeah, sorry about the interruption. So, the I have already created this cluster, which I'm using to run the jar file basically and the entire project. I won't the few things that I've previously done is I've already generated the key pair value for connecting to the SSH on Elastic EMR on EC2. And one other thing that um, I would like to specify is that I'm not using the S3 buckets for files at all. Okay, I'm using the HDFS that is inside the EMR, the EC2 instance basically, on which the EMR runs. So the only thing that I'm using the S3 bucket is for storing the jar file, and that is it. I'll now uh, for that I'll just quickly SSH into the just a second, into the server basically. Log in as Hadoop, and yeah, you can see that I've SSHed into it. The HDFS, all the directories are already created from before because I ran the job once. I'll remove it right now, except the input file. Mm. I've deleted all the directories. Let me just ls one more time root. And the only thing that I haven't deleted is the input one. Let me show you the file that is in the input directory. Yeah, so this is the file that is in the input directory. Let me just clear the screen really quick, and I'll just like to show you uh, the file that is in the input directory also. Okay. So yeah, the input file is there, and now I'll create the step for this. I'll just give it a name, LLM MapRed. I'll browse S3 and I'll point towards my jar file. And I've already written the required one. As you can see, I'm using HDFS for everything. I'm not using S3 buckets here. It's just, also I've chained all of the MapReduce, so it will just run one after the other. It will automatically take and process the data from the last MapReduce to the next MapReduce, and it will ultimately generate all of the outputs. Okay, so this setup is done, and I'll just add the step. Once this project will take approximately 30 minutes to run. So, and while that happens, I'll come back after the job has finished running. It's in running status. Yeah. Hi. So as you can see, the step has been completed. Let me show you the logs first. These are the logs, and as you can see, this is the map reduce for the tokenizer uh, class. This is for generating the embeddings. This is where it took the most time, as you can see. It started at 3:30. This is a GMT time, I believe, and it ended at 3:46. So almost 15 minutes. More than 15 minutes, yeah. Probably, yeah. So, and finally, there is a similarity map reduce. This also took a large amount of time. This is 3:46. It started at, and it ended at 3:55. So about 10 minutes. And yeah, it has finished. As you can see, similarity is generated. This was the last output, as you remember from. Yeah, this is the last output. So the jar is completed entirely, and now I'll show you. If you remember, all the output directories were removed from HDFS, and they're back. So I'll show you the final output. Yeah. Oh, uh, sorry about that. So the format of this one is basically this is the um, word with the token, and it generates the five tokens or words that is most similar to it basically. So this is one, and this one is format is word token and similarity. One is the highest similarity, so this is getting 0.98. So this is one word, this is another word, this is another word, this is another word, and this is the other word. So yeah, now let me show you. This is the output for the similarity, the last MapReduce. So let me just let me clear the screen. Let me show you the one with um this is, I believe, tokenized output, and yeah, we have three files. So I'll just do tokenize output, and I'll just print the head. Sorry, tokenize output, printing the head. Okay, this was not. I'll just print that out. Right? Yeah, this is a tokenizer output. I'll just explain what it is. The key is the line number. This is basically to preserve the order of the tokens, and all of the words are generated into tokens. That's it. This is the output for the first MapReduce, the tokenizer one, and here in the screen, and I'll show you the output for the embeddings. Embeddings. Out. So okay. So let's do embeddings output. I'll just do head in this case because not much is there. Yeah, it's a lot of data. So it's basically what it's doing is a token and its corresponding embeddings. If you remember, there was 10 dimension size from yeah, any dimension is 10. So one, two, three, four, five, six, seven, eight, nine, and 10. Yeah, and finally, just like just check one thing. Um, yeah, the word count is also there. So yeah, so this is the word count. This is the first one, the absolute first one where it's showing the word frequency and word count. This word has occurred 4 times, and the corresponding token is this one. So the first column in this one is the word. The second column is the frequency. So if you see Iraq, the word Iraq has occurred 36 times, and the token for the word Iraq is the corresponding, the third column basically. Another one, yeah, I'll also like to show you um, some words they have been like ipsy. There, some words are not in there in the vocabulary. So what JDocker does is it breaks the word so that it can be recognized basically. Indians, it's not a word, but yeah, like that. It has broken maybe something from minions. Um, yeah, there's a lot of words like this. So yeah, this is the my project, and yeah, that's it.